We have seen that the GAM defines the standard uncertainty as the uncertainty of the result of a measurement expressed as the standard deviation of a distribution of values. We have also seen that the GAM recommends as the ideal method for expressing measurement uncertainty a method capable of providing an interval built about the measured value to which a coverage probability or a confidence level can be associated, indicating the likelihood that the value of the measurement falls within that interval. We must therefore ask ourselves whether and how it is possible, starting from the standard uncertainty, to obtain a coverage interval. The definition of the interval is straightforward. You simply add and subtract the standard uncertainty u of x to the measured value xm, as you can see here. The real issue is how to assign a coverage probability to this interval so as to obtain the desired coverage interval. We have seen that the measurement result is mathematically represented by a random variable, which in turn is described by a probability density function. Referring to probability theory, it is possible to demonstrate that being x the values that can be attributed to the measurand and p of x the probability density function that describes them, the coverage probability of the interval from xm minus u of x to xm plus u of x is given by this equation. It is therefore obtained by integrating p of x between the bounds of the interval for which one wishes to evaluate the coverage probability. Geometrically, this probability is equivalent to the area under the probability density function over this interval, as clearly illustrated by the red-colored area in this figure, where a measured value of 1, a standard uncertainty of 0.05, and a normal probability density function have all been taken into account. In this case, the coverage probability assigned to this interval is 68.27%. It is intuitive to understand that this probability depends significantly on the probability density function. In fact, if we consider a uniform probability density function like the one shown in the figure with the same standard uncertainty, the coverage probability, still represented by the area shaded in red, is equal to 57.74%. Finally, to better understand the effect of the probability density function, let's consider a triangular function, again with the same standard uncertainty and therefore the same standard deviation, as shown in the figure. In this case, the same interval has a coverage probability of 65%. We can therefore conclude that it is possible, starting from the standard uncertainty, to build a coverage interval about the measured value, and that the coverage probability is strongly dependent on the probability density function assigned to the measurement result, varying, in the cases we have seen, from about 58% to about 68%. The question we must now ask ourselves is whether this probability is sufficient for the intended purposes. Let's recall that this probability expresses the likelihood that the true and unknown value of the measurement falls within the given interval. In general, a probability that does not reach 70% is not sufficient. To understand this, let us bear in mind that the probability of the measurement falling outside the interval thus defined is the complement to 100%. Therefore, if we use an interval defined by the standard uncertainty, the probability that the value of the measurement falls outside this interval is greater than 30%. This means that if we use that measurement result to make a decision, there is a probability greater than 30% that the decision will turn out to be wrong. It is therefore useful and appropriate to define intervals with a coverage probability greater than that associated with the interval built from the standard uncertainty. The GAM defines for this purpose the expanded uncertainty as a quantity that defines about the result of a measurement an interval which is expected to encompass a large fraction of the distribution of values that can reasonably be attributed to the measured. Similarly to what is recommended for the standard uncertainty, the GAM recommends using a capital letter U and no more than 2 significant digits to express the expanded uncertainty. Let us now see how to assess the probability that the value of the measure falls within the interval obtained by adding and subtracting the expanded uncertainty capital U from the measured value xm, as you can see here. The procedure is exactly the same as in the case of the interval built from the standard uncertainty. For example, let us suppose we again have a measured value equal to 1 with a standard uncertainty of 0.05 and a normal probability density function. If we consider an expanded uncertainty equal to 2 times the standard uncertainty, then the probability represented by the red area in the figure that the value of the measure falls within the interval xm plus or minus the expanded uncertainty is equal to 95.45%. Obviously, also for this interval, the coverage probability depends strongly on the probability density function considered. In fact, if we consider a triangular function like the one shown in the figure, for the same interval and standard uncertainty, the coverage probability is 96.64%. In general, the expanded uncertainty capital U is obtained, as you can see here, by multiplying the standard uncertainty small u by a numerical factor which the GAM refers to as the coverage factor. For a given probability density function, it is possible to associate a well-defined coverage probability with each coverage factor. This probability corresponds to the portion of the interval built about the measured value using the expanded uncertainty. In this table, the coverage probabilities associated with certain coverage factors are shown for the case of a normal probability density function. Note that these coverage probabilities are valid only in the case of a normal probability density function. To summarize, we have seen that by knowing the standard uncertainty and the probability density function used to represent a measurement result, it is possible to build an interval about the measured value. This interval represents the set of values within which it is assumed that the true value of the measure falls with a given probability. And this probability must be appropriate for the purpose for which the measurement result will be used.